At the dawn of the 21st century, after puzzling over the mystery of comets for 200 years, astronomers are ready to launch their most ambitious experiment yet. They call it Deep Impact. They are going to see what happens when a spacecraft slams violently into a comet at 23,000 miles an hour. Deep Impact's primary goal is to peer inside a comet. That inner material has remained relatively unchanged since the solar system was formed and could provide clues about the solar system's beginnings. But astronomers also hope to gather ideas about how to stop a comet heading toward us. Deep Impact began here at NASA's Vertical Gun Range in Mountain View, California, where it was the job of Dr. Pete Schultz and his team to figure out what the comet would do when it was hit.
This particular instrument allows us to fire a small sphere, about a quarter inch, at speeds that are maybe 6 or 7 times the speed of a rifle bullet. This whole assembly rotates up to an elevation where the gun is basically 3 stories high. This allows us to send the projectile through different openings in the chamber so that we can impact a flat surface at different angles.
Scientists believe comets vary in their makeup, so Schultz and his team built several different models, then hit each with shot from their ultra-high-speed gun.
The first scenario is what happens if we impact into something that looks like lunar dust. The second one is what happens if we impact into fluff. And the third one is what happens if we impact into a fluff covered with an organic layer. As we go down and look at the evolution of this crater, we find at the very end, after it's finished, we can still see the crater here. But in these 2 cases, when we're using fluff, we can't see the crater. It's completely masked.
The fluff completely absorbed the projectile, a frustrating result for scientists hoping to get a look inside. And there was another possibility Schultz had to consider. What if the entire comet is extremely fragile and porous? He searched for a substance for that simulation.
The comet may be sort of like a fluff ball. It may have been very low density. What do we do to try to simulate that? The best thing probably is a complex organic. What would that be? Cotton candy. We've got our comet made of cotton candy. Let's turn off the lights and let's get out of here.
The projectile soars right through the comet,
Can you back her up?
but the force shatters it.
Oh my God! There's no more comet, that's for sure. What a mess.
But this is not good news. A shattered comet can be even more dangerous than an intact one. The pieces tend to remain on the same path, turning one projectile into many. In 2005, once the team completes their tests, NASA is ready to take the plunge. It will try to drive an 820-pound impactor into a comet to find out what's inside. Deep Impact's principal investigator is the University of Maryland's Dr. Michael Ahern.
So here we have the model of both Deep Impact spacecraft. Many people think it was only one spacecraft, but it's really 2. The flyby spacecraft has all the instruments on this platform on one side, and if I turn it around, these are the solar panels that provide the electric power. Here's the impactor. That is 1/3 of a ton geologist's hammer with which you hit something to see how it behaves when you hit it.
January 12th, 2005. After 6 years of study and preparation, Deep Impact is ready for liftoff.
3, 2, 1. We have ignition and liftoff of a Delta II rocket carrying Deep Impact.
The spacecraft's destination is a 4-mile-wide comet named Tempel 1. Discovered in 1867, it's well known to astronomers. It orbits the Sun every 5.5 years and has lost much of its gas and ice.
People would argue that you should preserve the comets for posterity, but doing a violent study on one that is just typical of a whole class seemed to us to be the right choice for science.
Deep impact takes just 5 months to reach Tempel 1's orbit. On July 2nd, 2005, it turns and points its cameras at the comet, 500,000 miles away. Then it releases its impactor. If all goes well, the collision will blow a hole in Tempel 1 about 600 feet across and 5 stories deep, about the size of the Roman Colosseum. But it's stories deep, about the size of the Roman Colosseum. But it might destroy the comet by breaking it apart. Back on Earth, hundreds of scientists hold their breath.
We lost signal, and we had to stand there and wait around. So everybody was trying to be, go keep busy and not feel anxious.
But just in time, the signal returns.
Yes.
The energy went in, bounced back, and drew out all this material from beneath the surface, which was then exposed out in space into sunlight. And so this is scattered sunlight off of all of this debris that was excavated from the interior of Comet Tempel 1.
The half-mile-wide comet and NASA's 820-pound craft have collided at 23,000 miles an hour. The explosion is equal to nearly 5 tons of TNT. It completely vaporizes the impactor, and it kicks up far more dust than anyone expects.
One of the reasons it was so dusty is that the particles were much smaller than we thought. This is a very fluffy body.
The amount of dust is a telltale clue to the comet's makeup. Tempel 1, at least on the surface, contains far less ice than scientists expected.
There was no way that there were large blocks of ice anywhere or rock. And that really is helping us formulate, how did these comets get put together? How did they break up? This is the first data we've ever had. So in that sense, it's revolutionary.
Analysis of the dust showed molecules containing carbon, organic material. So it's plausible that comets could have brought such material to Earth early in its history. A return mission is planned to take another look.
In 2010, NASA will have redirected the Stardust spacecraft to go back to Tempel 1 and look for the crater that we formed to see what happened to the surface and the rest of the comet when we impacted it.
Scientists hope to learn something else from deep impact. Clues knocked Tempel 1 into a slightly different orbit. But the comet has continued on exactly the same path as before. Harder.
Let's assume that this is the cometary nucleus. One way of slowing it down and having it miss the Earth in 20 or 30 years' time is to simply run into it. Bam. If that doesn't work, do it again. If that doesn't work, do it again.
But some think we'll need a more radical approach. One plan calls for detonating a nuclear warhead near a comet to nudge it onto a different path. Controversial proposal because of the unknown consequences of releasing radiation in space. Others have called for drilling into the nucleus and setting off a blast inside. But as we've seen, this has the danger of turning one deadly projectile into many. The pieces could continue on the same orbit, and like the blast from a shotgun, wreak destruction over a wider area.